So inverse variation. Inverse variation is a relationship that's written in this form here, that y equals k over x. So it's similar to direct variation, what we just looked at those two problems with, except for direct variation is a linear relationship, where inverse variation is basically the relationship is dividing. So this means that when x gets bigger, then y is going to get smaller. And when x gets smaller, y is going to get bigger. Well, and that should make sense, because if I divide by a bigger number, I'm going to get a smaller number. And if I divide by a smaller number, I'm going to get a larger number. The constant k is called the constant of variation. And that's always going to be, you'll have a specific number that you can use to get that. Inverse variation implies that one quantity will increase while the other one decreases. And if we multiply both sides by x, we get this relationship here. So we have two relationships that we use with inverse variation. One, to be able to find k, and that's established by multiplying x times y. And the other one, which is the general form, if we're going to graph it, is y equals k over x. And that's also written in this nice, lovely box here. So we're looking for, when we're looking at a specific problem, we're looking for it to say that y varies inversely as x does, or it might say y is inversely proportional to x. So if we're trying to establish whether these relationships represent an inverse variation, then all we're going to do is we're going to multiply the values of x and y. Because x times y should equal the same value of k. If you get the same value when you multiply, it represents an inverse variation relationship. If you don't, then it's not. So 1 times 30 is 30. 2 times 15 is 30. And 3 times 10 is 30. So since these are all the same, then this is an inverse variation. I spelled it right. This data represents inverse variation. Where in part B, when I multiply them, I get 5, 20, and 80. Since they are not the same, then it's not an inverse variation. So if you can multiply x and y together and get the same number, it represents an inverse variation relationship. And if you multiply them together and it's not, then it wouldn't be one. Okay. When we did direct variation, we divided them, where with inverse we're multiplying. Okay. All right. So letter C here. Is this an inverse variation relationship? Nathan, what do you think? Is it or not? Why not? Okay, that's good response then. Okay, tells me whether you got it or not. Alex, what do you think? Why? Okay. He thinks it is, but he's not sure. Anybody know why? Okay, so let's divide by 2. So we get x, y equals 14. Okay, does that make it an inverse variation relationship? Am I multiplying x and y together and getting a constant? Yes, so this is. All we're looking for is it y? I have 2 things I'm looking for. I'm looking for x times y equals a constant k, or that y equals k, some constant over x. If I have either of those situations, then it is an inverse variation. If I don't have them, then it's not. Since k is a non-zero constant, x times y cannot be equal to 0. Therefore, neither x nor y can equal 0. So no solution points will ever be on the x or y axis. So here are some examples of some graphs. The blue one goes together. Or let's go with the red one first. The red one, y equals 1 over x, that's called the parent function for inverse variation. And then we have in blue, we have y equals 5 over x. And in purple, y equals negative 2 over x. So the graphs of inverse variation is either going to be in the first and third quadrants. Okay, everybody knows the quadrants, right? Okay, if you don't remember what they are, this is 1, 2, 3, and 4. Okay. So if k is positive, it's in the first and the third quadrants, because here our value of k is 5 or 1. If k is negative, negative 2 over x in this case, the purple graph, then the graph is going to be in the second and the fourth quadrants. Okay, so when you're graphing these, all right, so this is a note for you then, okay, is that if k is positive, so when k is greater than 0, we're going to be in the first and third quadrants. And when k is less than 0, it's the second and fourth quadrants. Okay? And the graph's always going to be curved like what those are. Okay? And I'll show you why that happens in a moment. All right? So example 2 says write and graph the inverse variation in which y equals 0.5 when x equals negative 12. So to write an inverse variation rule, we're trying to get y equals k over x is what all of our rules are going to look like. So what we need to do is we need to know the value of k. And how do we find k? We multiply what? X and y together. Okay? So x times y equals k, so 0.5 times negative 12 equals negative 6, right? Okay. So my inverse variation relationship then is going to be that y equals negative 6 over x. Okay. This is my rule for the inverse variation for this problem. So I have to draw a graph. Okay. All right. Now, to draw a graph here, I wish that fly would stop flying by there. Okay. To draw the graph then, we know that since k is negative, that my graph is going to be in the second and fourth quadrants. Okay, so it's going to look similar to that purple one. Okay, well, how do I know where it's going to go? Oh, I got another example up there. Well, here's what we do. Okay, we'll make a table. Let me find my table. That's not what I want. I don't want the table. Here we go. All right, so we're going to make a table. Is that somebody's phone? It's not coming from over there. All right, so here's what we're going to do. When we make the table, we want to use the factors of 6. What are the factors of 6? The factors of 6. 2 and 3, or 1 and 6. Okay, nice try. Those would be multiples of 6. We want factors of 6. 1, 2, 3, and 6. All right, and we're going to do positive and negative. All right? So we'll start out and we'll make a table, and we'll do negative 6. Oh, come on, get there. Negative 6. And what's negative 6 divided by negative 6? 1. Okay. And then we'll do negative 3. And what's negative 6 divided by negative 3? 2. And we'll do negative 2. And negative 6 divided by negative 2? 3. Okay. And then we'll do negative 1. And negative 6 divided by negative 1 is, oops, not a 16. Okay. 6. All right, so there's our part of our table there. Okay, we use using the factors of k to make our table. All right, so now we'll use positive numbers. All right, so positives. Let's see, let's go positive 1. What's negative 6 divided by positive 1? Negative 6, okay? And positive 2. What's negative 6 divided by positive 2? Negative 3. Okay. And then we'll do positive 3. Negative 2. Okay. I think there's another one down there, so we'll see. No, it won't make another one. Okay. So then we would add another one and put positive 6. And negative 6 divided by positive 6 is negative 1. Okay. All right. So we make a graph. So we plot those points on my graph. Oops. There we go. Okay. All right. So where did I get these numbers from again for the x values? They are the factors of k. All right? They're the factors of k. And so then I would just draw my lines. Let's see how good I am today. It's pretty good, huh? Man, I got perfect lines today. Okay? And then the one thing is we need to remember to do what? Remember, these lines go on forever. So these are arrows. Do they cross the x or y axis? No, because I can't divide by 0. Okay? So, we're writing and graphing the inverse variation. That means that we need something that looks like this. Y equals k over x. That's the rule we're looking for. The value of k is found by multiplying x and y together. So once I find k, I write it as y equals k over x. And then I need to graph it. Okay, when I'm graphing it, the values I choose for x are going to be factors of k. And then we plug it in. Okay, Morgan? Okay, so let's look at a story problem that involves an inverse variation relationship. So here it says the inverse variation xy equals 350 relates the constant speed x in miles per hour to the time y in hours that it takes to travel 350 miles. Determine a reasonable domain and range and then graph this inverse variation. Use this graph to estimate how long it would take to travel 350 nukes driving 55, I think that means miles, driving 55 miles an hour. Okay. So what would be a reasonable domain and range? All right, let's talk about domain first of all, values of x. So x is speed. Okay. So what's a typical speed that people drive? 55? Okay. All right, if I was going 350 miles, you think I'd drive 55 miles an hour? Okay, all right. But that's only one number though, okay? What's the slowest that people usually drive? You drive around town, how fast do you drive? Okay, around 25, right? Okay, how many of you have your driver's license or a permit where you get to drive with your parent at least? Okay, most of us do, okay? And so you very rarely drive 25, right? But that's about the slowest that you probably go when you're driving around town, right, Megan? Okay? And then your parents take you out on the highway to drive, or you get to go out on the highway to drive, and out there you drive about how fast? 70. Some of you, maybe parents might let you go to 75, right? How many of you parents let you drive 75? Okay, your dad lets you go faster than 75. Okay, I'm staying off the road when you're out there. Okay, so our domain then, our values of x are probably going to be greater than or equal to 25, but for sure greater than 0, right? Because you never drive 0. If you go 0 miles per hour, how far are you going? Nowhere, okay? All right, and then we probably drive, somewhere around 75, maybe a stretch 80 miles an hour. Okay? So to go with that domain, we need a range that goes with that also. Okay, so this is our domain. Now, how would we find our range, which is the y values? How do we find the y values then if we know the x values? Okay, we can substitute the numbers in for x and divide, okay? So, since we're dividing, our smallest number for y is going to come from the 80, right? So who can tell me what's 350 divided by 80? 4.375. So how about if we say that we'll just say that y is greater than 4, okay, right? Because we like whole numbers if whenever we can use them. Okay, and what's 350 divided by 25? No, it doesn't go into the 80, and I'll show you why. What? 14. Okay, it doesn't. The 4 doesn't go under the 80 because we always have the smallest number on the left and the largest number on the right. Okay, so this would be our domain and range. Now everybody's going to be a little bit different, but you have to think through it a little. Okay, domain and range. Okay, so then they want to know, okay, how long does it take them if they're driving 55 miles an hour? So at 55 miles per hour, my time would be what? Somewhere between 4 and 14, right? Can you tell me exactly where between 4 and 14? How, Nolan? Not using the graph? We didn't make a graph, did we? Isn't there an easier way than the graph? How did you get 4 and 14? Okay, you divide 350 by those two numbers, 25 and 80. So if they're going 55 miles an hour, then how long is it going to take them? 6 point what? 6.36 hours. Okay. So that was found by doing 360 divided by 350 divided by 55. Okay. All right. So you have some questions where you're going to have domain and range involved in them, so you'll have to do a little work with them. All right. And you just have to think realistically. When they ask you for a reasonable domain and range, you got to be realistic, okay? You can't say that, well, my domain here could be 100, okay? I mean, how realistic is somebody's going to be driving 100 miles an hour? You know, unless they're out on the Autobahn or something like that, or out in the West somewhere where you know what I'm talking about, then don't I? Don't you? How fast do people drive on the Autobahn? Hmm? No, normally 100 to 200. 200 is very fast. Anybody know what kilometers compared to? Okay.
133. 200 kilometers is about 130
miles an hour. Yep, okay. Yep. So, and they, I mean, you have to have a car that goes that fast, but because of, have you been out there driving that fast before?
I haven't tried, but my parents normally drive around 100 miles.
Oh, 100 miles per hour. Okay. All right. Now you have two, right?
Yeah, in Austria, like the highest you can drive is 130 kilometers.
Okay, which is about 100 miles an hour then.
Yeah, probably. It's about 80, 85.
80, 85. Okay. All right. And there's some parts of the United States out in Montana and that area where it's very flat, and their speed limits are actually quite a bit higher out there too. And during those, because it's long distances and there's nothing there, right? You go a long way and you don't see anything, correct? On those highways where they drive really fast. You see lots of other cars. Do you see wild animals? Oh, okay. All right. No deer? Okay. People don't run into them like they do here then. They're not laying all over the road. Okay. All right. Okay. All right. So, you know, you have to have realistic ones. If we were driving at the Autobahn, we would have different reasonable domain and range. Our domain would go much higher. Okay. All right. So, we have a product rule for inverse variation. This product rule says if we have 2 points, okay, x sub 1, y sub 1, and x sub 2, y sub 2, then we can use this product rule for inverse variation to solve for missing values. And this actually works really well for story problems that involve inverse variation situations. So we're going to use the product rule when we know 3 parts and we want to find the 4th. You can use just a regular inverse variation formula, but it's much easier if you use the product rule. So in this example, they tell us what x sub 1 equals, x sub 2, and y sub 2. And they let us know that y varies inversely as x does, and that's very important. Because if it said it varied directly, then that would be a whole different situation. And they want us to find y sub 1. So here's our rule. Now understand that this is legitimate because both of these things just represent k. Because if it's an inverse variation relationship, anytime I take 2 points of that relationship or a point and I multiply the x and y values together, I get k. So it doesn't matter whether it's the first point or the second point. When I multiply them, I'm going to get k. So then it's just a matter of plugging in the numbers and solving. Oops. But make sure you plug in the right numbers in the right spot. All right, so x sub 1 is 5. X sub 2 is 3. Y sub 2 is 10. And we're going to find y sub 1. All right. So then we just divide both sides by 5. And get that y sub 1 equals 30 divided by 5 is 6. So if I put them back in, 5 times y sub 1, which is 6, is 30. And 3 times 10 is 30. So in this problem, we could even go so far as to say that k is equal to 30. Because for both points I am dealing with, when I multiply x and y together, I get 30. Okay? I'm not going to go that way now. Okay, let's stop here.